2.4 is on linear functions and slopes. So we're going to start out by thinking about a line and the graph of a line, okay? So let's look for a moment at a quick graph. And let's say we had a line that was rising to the right here, something like this. And let's say I took 2 points on that line, any 2 points I wanted. I'll pick a point here, I'll pick a point here, okay? Now between these 2 points, you can form a right triangle simply by extending from one point over to the right till you get directly beneath the other point, and then extending this down. Okay, and there's my right triangle. Now you can form a right triangle between any 2 points on this line, right? So I could take a different point, I could take a point somewhere in between here and draw another right triangle. Or I could try a completely different point, maybe one out here, and draw a right triangle to that middle point. And so there's a whole bunch of right triangles up here. What's interesting about the right triangles is because this slope, or because this is a line, okay, so the angle doesn't change, we have every triangle in here is a similar triangle. The sizes might be different, so you get this first one I drew is a bigger triangle than the last two, but they're similar triangles in that all of the angles, the corresponding angles, are congruent, okay? So you obviously have your 90-degree angles, but the lower left angle in each of those triangles will be congruent, and the upper right angle in each of those triangles will be congruent. So that gives you similar triangles. And the neat thing about similar triangles is that corresponding sides are proportional to each other, okay? So you can set up ratios between the corresponding sides, and the ratios will always be equal. Okay, so that's just a quick summary, just using some triangles here, but now let's actually put some numbers in it, okay? So let's say I had some points here. Actually, I'm going to redraw this and put some numbers to it. All right, so this time, let's say we had, now in order to get a slope, you have to kind of go up at the same rate between each point. So let's say, I'll throw some tick marks in here. We'll number them just using whole numbers, and then maybe we'll do the same going up. One, two. Okay, let's go ahead and throw some points in there, like at, let's do 1, 1. Let's do 2, 3. So basically what's going on here is I'm going to go over 1 and up 2, and that'll give me, if I continue that pattern, it'll give me a nice straight line, or it should. All right, so over 1 would be 3, up 2 would be 5. Sketch this in as closely as I can, and then kind of erase those. 4 and up to 7. All right, and maybe I can get one more in there. Over 5 and up to 9. That looks pretty good. Okay, so I've got 1, 2, 3, 4, 5 points in there, and now I'm going to draw a line to connect those points. No, not a perfectly straight line, but pretty close. I may have to move a couple of those points just to get them to line up, and of course I'm going to make this go left. Oops. Again, not very straight. Redo. Much better. Okay, so there's our line. And again, I'm going to put all of these ordered pairs on here. 1, 1, 2, 3, 3, 5, 4, 7, and 5, 9. Okay, so again, at each of those points, you're moving over 1 unit, up 2, over 1, up 2, and that gives you that consistent slope. Okay. All right. And so now let's take a look at some of those similar triangles I mentioned at the beginning. Let's go with a triangle that's formed between the point 2, 3 and the point 5, 9. Okay, so let's look at that one. And then let's also look at the point that goes from, let's go 1, 1 to 3, 5. So we'll take this triangle here. And maybe we'll do the one from 2, 3 to 3, 5 as well. Okay, so we'll do 3 different triangles and we'll just kind of look at some of the ratios. The ratios that we can, or the side lengths that we can easily determine are the horizontal leg of the triangles and the vertical legs, okay? The hypotenuse, we would have to use the Pythagorean theorem to find those, so I'm not going to worry about those. It's a little bit easier just to work with the horizontal and the vertical sides. So if I look at, let's say this big triangle here, the one from 2, 3 to 5, 9, okay? So 2, 3 to 5, 9, so that triangle. Let's look at the length of the vertical side for a moment. Okay, the vertical side here, I'll abbreviate. Vertical side runs basically from a height of 3 up to a height of 9, okay? Essentially, it's the difference between the y values of the 2 points. To find that length, well, you would take the final value minus the initial value. 9 minus 3 gives you a distance here of 6, right? So this height would be 6, and again, it's the difference in the y values. So the vertical side is 9 minus 3, which is 6. The horizontal side, again, just going from the 2, 3 to the 5, 9, is going to go, it's going to start at the 2, it's going to move over to the 5, okay? And so again, let's do horizontal side. Again, I'm abbreviating a little bit here. From 2 to 5, we know that that's an increase of 3, right? So this side here increases by 3. And so the reason for that is, again, we take the final value minus the initial value, 5 minus 2, and that gives us our 3. Now I said that if you take ratios of corresponding sides with similar triangles, the ratios are always equal. What we're going to do is we're going to divide those two. We're going to take a ratio of the vertical side divided by the horizontal side, okay? And now that ratio is going to be 6 over 3, which reduces to 2, okay? So that gives us the ratio between the vertical and horizontal side. Basically, that means the vertical side is twice as big as the horizontal side, okay? All right, now let's repeat this process, but for a different combination or a different triangle, okay? So it'd be a different combination of sides is what I was trying to say there. Let's try the point 1, 1 to 3, 5. Let's do this sort of middle-sized triangle here. So from 1, 1 to 3, 5. So again, I want to find my vertical side. In this case, the vertical side runs from a height of 1 to a height of 5. So you start at 1, end at 5. We subtract in the other order. So we do 5 minus 1, which is 4. Okay, So that has a height of 4. I'm not going to write it all in, it's going to get real crowded there. The horizontal side is going to start at 1 and run to 3, okay, in the x direction. So again, we subtract 3 minus 1, that gives us 2. And then I said, well, the ratio of corresponding sides should be equal between similar triangles. So in theory, when I create this ratio, vertical to horizontal, I should get the same answer. And so when I do ratio, let's do vertical side over horizontal. You guys can probably already see this developing. It's 4 over 2, which of course reduces to 2. And it's the same ratio that we got before. Again, meaning the vertical side is twice as long as the horizontal. Try this one more time with that third triangle, the little one I just put in there. So we're going to do, let's see, it's from point 2,3 to the point 3,5. Okay. Again, we'll set that up looking at the vertical side. And for this small triangle, the vertical side starts at 3, goes up to 5. That's a height of 2, right? From 5 to 3 or 3 to 5. So we'll subtract them in reverse order. Okay. 5 minus 3 is 2. The horizontal side for that starts at 2 and goes to 3. So it'd be 3 minus 2, again in reverse order, which of course equals 1. And when I set up my ratio, the ratio of corresponding sides, which is vertical to horizontal, that in this case is going to be 2 over 1, which of course reduces down to 2. Again, all three of these, the ratio of the vertical side to the horizontal side is 2, or 2 to 1, which basically again means that the vertical side is always twice as big as the horizontal. This works for every pair of points. They don't have to be even integer. They don't even have to be integers. They could be anything. Any point in between these, decimals, fractions, doesn't matter. I just chose nice ones to work out the arithmetic. But no matter what 2 points you choose, even if they're negative, even if they're like thousands of units out, way out there somewhere, the ratio of the vertical side to the horizontal side will always be the same. Okay, and for that reason, we give it a name. Okay, and the name of that is called the slope. So the slope is by definition the ratio of the vertical side, or the vertical change, I should say, to the horizontal change on a line. Okay, so that's the definition of a slope. Right. Now, we often use a variable or a letter to represent the slope. It's a little bit weird, but we use the letter m. Okay, so the letter m is always going to be equal to the vertical change over the horizontal change. Okay, so it's a fraction where the vertical change is divided by the horizontal.